Here is your video on determining the reaction order based on data of concentration versus time, especially using Google Sheets. So what are we doing here? We have this data, we have time, we have concentration data. So this is different than our method of initial rates where you actually get the rate with respect to the concentration of the reactants. We need to actually graph here. So this is the way to experimentally determine the reaction order based on this type of data, like you might be doing in a fading of crystal violet lab, right? So here's what we have. What are we trying to figure out? The next step here, after you get the order, is to write out the rate law and calculate the rate constant. So let's just put this into perspective here. The rate law is going to look like this. It is always rate equals K. Always. The rate constant is there. Its units might change, but it's always K. And then it's multiplied by the concentration of the reactants. In this situation, this reaction is the decomposition of a single reactant, that N2O5. So we'll just pop that in right there. What we do not know is we do not know the exponent, which represents the reaction order. So we don't know how much the concentration affects the rate. That's what we're graphing to find out, okay? So let's just see. We have some options. There are three different ones. If the graph of concentration versus time is linear, that means it's 0th order. If the graph of natural log of concentration versus time is linear, it means that it's 1st order. If the graph of 1 over the concentration versus time is linear, then it's 2nd order. So all we need to do is do the calculations to get the data into the natural log and into 1 over. So let's just set this up, equals natural log, take the cell we want to do the work on, nope, wrong, equals natural log, there we go, thank you, and then we're just going to drag this down, get it to populate. Okay, let's do this again over here. So equals 1 divided by, and that 1 is how you tell Excel or Google Sheets that you want it to do some math for you. So 1 over B3, let's just drag this down. So I think what's easiest is to just look at it all at once and see if you can just auto cut anything out. So I'm going to highlight all of this. And I have those titles on there just to make it easier to see what we're doing. I think it's nice when you're graphing. Okay, so it auto made this column chart for us. Ugh. Scatter plot, always please. Okay, so we're looking at this. We got some weird stuff. It made time for us. So let's make sure that time is on the x-axis. There we go. And I don't need time versus time. That means nothing to me. Okay, so just looking at this data initially, those yellow dots, not a linear relationship. So that's 1 over the concentration. So let's just delete that from our comparison here. We know it's not 2nd order, it's not linear. Now, both of these look pretty linear. Can't really tell from a visual inspection. So let's go over to customize, series, trend line, get me that label, use equation. Here's what I really want. I really want that R squared. So here's what we have, 0.948 for concentration versus time, R squared equals 1 for the natural log of concentration. Did somebody make this data up? They must have. So that's looking good. That looks like that's our actual linear relationship. So let's just get rid of this. So now what that is telling us is that it is a 1st order reaction. So now we know up here, we know that that question mark is actually to the 1st power, which I'm not going to write in because we understand if that everything is to the 1st power if it doesn't have a different exponent, right? So that's what we know right now. Our next step of this is to then figure out K. So what's really nice, remember our integrated rate law works with Y equals mx plus b. You know what I mean? Okay. And so what we have over here is that the natural log of our concentration of reactant at time t is equal to negative KT, and then we have our natural log of the concentration at time 0 over there for B. So what we know is that the slope of this line is K. And the slope is going to be negative. It's negative K. So in order to get K, we'll need to get rid of that negative sign. So it looks like the slope is negative 4.83 times 10 to the negative 4th, right? Pretty nice. So we now know that our rate constant is 4.84, and I'll use the computer language because I don't have exponents, okay? Multiplied by our concentration of N2O5 to the 1st. Cool? So we figured it out. We can do a lot of math there now. We can figure out the rate. We can do lots of different things. Okay, let's try this on another data set just to see how we're doing. Okay, so this is data set 5, and we need to do the same thing. ln of that data, enter. Yeah, autofill, thank you. Equals 1 divided by that data set. Autofill for show. Now, chart. Oh, that was not good. Whew. Get rid of that chart. Let's not even do that. Let's highlight. Okay. Let's make our chart out of everything. Again with the columns. Okay, we got our scatter. Ooh, I can't rule anything out. Let's just make sure that I chart everything correctly. Okay, so if it's linear, blue is 0th, first, second order. Let's just customize. Let's get those R-squared values. I don't want to think too hard. Trend line. Let's get that R-squared. Okay, who's the best? Ooh, 1 over the concentration. So it looks like our second order is the best, and I turned on those equations so we can get K really easily, right? Let's just remove that. Let's just remove that. So, oh, no, I didn't turn on the equation. Sorry. Let's do it. Please use equation. Okay, 0.0131. So in this case, let's look at our rate law. Let's type it out. So we know rate is always equal to K, but K in this case, we figured it out. It is 0.0131, okay? And then we are going to be multiplying that by our C4H6. Again, with just respect to 1, keeping it easy. And then that is a second order reaction, so I will just use my little caret and say it's to the side. So that's our rate law. Hope that helps. Let me know if you have questions. Nice job, APChem. Hang in there. You're champions.